Before we talked about the geometric side of working with vectors, but now we want to talk about the numerical side. Unfortunately, while the geometric way of working with vectors is pretty cool, it's just not all that useful. With simple vectors, the geometric way can work out pretty well. But vectors that are even a bit more complicated can make the process pretty frustrating. In practice, it's usually pretty difficult to add vectors geometrically, but it's never difficult to add vectors numerically, so how do we do that? Let's move to 3 dimensions and think of a 3-dimensional vector. Now imagine this vector has its tail sitting at the origin. If we want to find some numerical representation of this vector, we need 3 different numbers to sufficiently describe the vector. Lucky for us, 3 numbers that work really well here are the x, y, and z coordinates of the tip. With the vector sitting at the origin, these numbers completely define the vector. No other collection of 3 coordinates will give us an identical vector sitting at the origin. But now suppose that the vector is not sitting at the origin. Now we run into a bit of a problem. You see, the x, y, z coordinates of the tip of this vector are not the same as the x, y, z coordinates of the vector's tip back when it was sitting at the origin. That's kind of problematic considering this is really just the same vector, but just moved to a different point. So we need to come up with a different way of describing this vector. So now we're going to talk about unit vectors. They're going to help us resolve this conundrum. A unit vector is just a vector with a magnitude of 1. You can also see we denote unit vectors with a cute little party hat on top of them. We call this vector over here u hat. So that gives us the ability to define 3 really useful unit vectors. The I hat unit vector is just a vector that points along the x-axis and has a magnitude of 1. The j hat unit vector is just a vector that points along the y-axis and has a magnitude of 1. And the k hat unit vector is just a vector that points along the z-axis and has a magnitude of 1. So a useful way of describing vectors comes about by adding up these unit vectors in different ways. So for example, what if you take I hat minus j hat plus k hat? Remember, if you want to subtract j hat, you can just think of it as adding negative j hat. And you end up with this new vector that we see on the screen here. This right here is I hat minus j hat plus k hat. Note that this is actually a complete definition of the new vector we have. The new vector is 1 I hat minus 1 j hat plus 1 k hat. With these 3 numbers, 1, negative 1, and 1, we are completely defining the new vector. So now we can take this a bit further and ask ourselves, how can we use I hat, j hat, and k hat to describe any vector? Well, our original vector was sitting at the origin and had x, y, z coordinates of 7, 3, and 2. So if moving 1 in the x direction gave us 1 I hat, then moving 7 in the x direction gives us 7 I hat. And moving 1 in the y direction gave us 1 j hat, so moving 3 in the y direction should give us 3 j hat. We're almost there. All we have to do now is move 2 in the z direction, and we need 2 k hat to do that. So we're left with the addition of these 12 vectors giving us our resultant vector. I hat plus I hat plus I hat plus, and so on, gives us 7 I hat plus 3 j hat plus 2 k hat. We've constructed a numerical representation of this vector based off of unit vectors that never change so long as our coordinate system doesn't change. You see, if we move this resultant vector off of the origin to some other arbitrary point, we can still use the same representation because it doesn't depend upon the vector being at the origin. Unit vectors still add the same way even if they're not at the origin. So no matter where this vector is sitting, a reasonable way of representing the same vector is given by 7 I hat plus 3 j hat plus 2 k hat. And that means we now have a useful way of representing any vector that exists in 3-dimensional space. A simple heuristic you can use is if it's sitting at the origin, you just take its x-coordinate, y-coordinate, and z-coordinate of the tip, and those are now the I, j, k components of the vector. If the vector is not sitting at the origin, however, all you have to do is figure out what its x-length is, what its y-length is, and what its z-length is, and each of those becomes a component of the vector respectively. So now that we can represent any vector as something I hat plus something j hat plus something k hat, How do we go about working with vectors numerically? If you want to add these two vectors, for instance, you can just add their components separately, and you end up with the resultant vector. Here, let's try it out. If you take -7 and add it to +5, you're left with the I hat component of the resultant vector, which is -2. Similarly, if you take +1 and add it to -9, you're left with the j hat component of the resultant vector, or -8. Finally, if you add the k hat component of the first vector, which is -2, to the k hat component of the second vector, which is -3, you're left with the k hat component of the resultant vector, or -5. Subtraction works pretty similarly too. If we want to subtract this vector from that vector, all we have to do is subtract each of the individual components, and we're left with the resultant vector. At this point, it might seem less visually obvious what's going on, but it's certainly much easier to do on paper than trying to graph some three-dimensional thing and subtract it from some other three-dimensional thing. Don't you agree? In the next video, we'll talk about some visual implications of all this. Now, what about multiplying a vector by a scalar? All we have to do is multiply each component by that scalar, and the resultant vector follows. For instance, if we take this vector over here and we want to multiply it by -3, for example, all we have to do is take each component and multiply it by -3. Finally, if we want the negative of a vector, all we have to do is evaluate the negative of each component, and we're left with the negative of that original vector. Another way of looking at this is we're just flipping the sign of each component.